So good evening all. So today we are going to discuss about the week 2 lectures. First I will start with the so in the last week we studied about the TPRE mechanism and IIT theory, which is impurity induced theory. So in that we use the modifier atoms to restrict the growth of silicon crystals, that is not that is that hampers the mechanical properties of aluminum silicon alloy. Means try to modify the microstructure uh, by from flaky nature of silicon, eutectic silicon, to fine fibrous structure. So in that, so the IIT theory says that that is impurity induced theory, in which modifier atoms like sodium are added so that absorbs to the stubs and kinks on the silicon crystals, on the silicon crystal nuclei, and restrict the growth of the and restrict the silicon attaching of silicon atoms. And the modifier atoms are able to branch the fibers that enables the growth in all directions, that reduces the tendency of flaky nature. In the TPRE mechanism, in these, and the second mechanism is the TPRE poisoning theory. TPRE means twin plane reentrant edge. Edge growth. So in the TPRE poisoning theory also we use modifier atoms, and that modifier atoms restrict the silicon attachment of silicon atoms to the reentrant edge. Reentrant edge, and and selectively and restrict the growth and restrict the anisotropic growth of silicon. The reentrant edge, so because the reentrant edge are considered as the favorable site for silicon atoms, therefore modifiers literally deactivate the TPRE mechanism. Restriction of rapid growth along so the silicon tetrahedron makes the twin nuclei on the other tetrahedral site. So this direction is 211. So the anisotropic growth occurs along this direction. So the anisotropic it reduces the modifier atoms enables the isotropic growth of the nuclei, and they reduce the flaky nature. So another good evening, Digambar.
Yes, ma'am.
Is there any more people who wants to join the meeting, or we can continue?
Yes, ma'am.
Means there are no people to join. Other
No any people, ma'am, to join on this time.
yeah. So I will explain the I will give the overview of the this week of the last week, in which we discussed about the modification theory of the aluminum silicon alloy network, and the rod designation of wrought alloys and cast alloys, further than the strengthening mechanisms. So do you have any doubt, or I can continue?
No, ma'am. The previous lecture to be not attended by me because of I am going to out of nations, ma'am.
Okay, okay. Okay, then I will explain through from starting. Okay.
Okay, ma'am.
Okay, so yeah. So first, do you know about the TPRE mechanism or IIT theory, which in the first week? Did you attend that first week lectures, or Digambar?
Yes, ma'am.
Means I'm asking that are you coming first time, or did you attend the week one lectures, or,
No, ma'am. I will attend to first time your lectures online.
first time? Means you did not attend any lecture from lecture
No,
one.
yes, ma'am. No, ma'am.
Okay,
First time it to be attend will be to be attended tomorrow today lectures.
okay. No, the tutorial lecture means I mean to say that you did you go through the professor's lectures from of the week one and week two?
No, ma'am. No, ma'am. Sorry to ma'am. I will we will to know no to be continue to join to week one to week two because
Oh,
up to official work to be going to out of station, ma'am.
okay, okay, no problem. So
Sorry, ma'am. To be absent to be week one week two lectures.
no, no. So I will explain the week one lecture if you want.
Yes, ma'am. Okay. Thanks, ma'am.
Okay. So just wait. is there is only one. So in the first, as we know that the aluminum alloys are preferred above the other ferrous alloys because of the it has the low density of 2.7 gram per
Yes.
cc.
Okay, miss. Yes.
Yeah. So the do you know the steel's density for iron?
7.86, ma'am.
Yeah, 7.86 gram per cc. So it is
Gram per centimeter.
so the difference between densities is very significant. Means it's 7.86 from 2.7. So the lightweight enables the application of aluminum alloys in the automobiles and aerospace because of its low density.
Yes, ma'am.
And the melting point of aluminum is 659 degrees Celsius.
Yes.
Boiling point is 2270 degrees Celsius.
Yes.
The thermal conductivity is is 237 watt per meter Kelvin. And the thermal expansion coefficient is 23.5 into 10 raised to power minus 6 ohm centimeter. And the resistivity of aluminum is 2.65 into 10 raised to power minus 6 ohm. This is ohm centimeter and this is per Kelvin. So the electrical resistivity of aluminum is also very low. So that's why it gets the application in electrical appliances. And the crystal structure of FCC is crystal structure is FCC of L. And then the lattice parameter is 4.05 angstrom. Atomic number of 13 and atomic weight is 26.9. Rohan, did you attended the week 1 and week 2 lectures of Professor Ranjit Bori, sir? Rohan, I'm asking to you.
Hello.
Uh,
Actually, I did not attend.
means no lecture you attended.
Yeah, not here today. Not today.
Yeah, okay. Then, Digambar also did not attend any lecture, so I'm explaining through from the lecture 1. It's fine.
Yes.
Okay. So the aluminium properties has the like its density is aluminium is the non-ferrous metals. So it has the density of 2.7 gram per cc, which is very significantly lesser than the steel and other metals. The melting point of aluminium is 659 degrees Celsius. The boiling point is 2270 degrees Celsius. The thermal conductivity of 237 watt per meter Kelvin, and the thermal expansion coefficient is 23.5 into 10 raised to power minus 6 per Kelvin. Electrical resistivity, it has the 2.65 into 10 raised to power minus 6 ohm centimeter. So the properties of aluminium enables its application in mostly because it has lightweight. So automobiles and aerospace application is the application use the aluminium extensively. The crystal structure of aluminium is FCC. Lattice parameter is 4.05 angstrom. Atomic weight 13. Sorry, atomic number is 13 and atomic weight is 26.98. And it is paramagnetic in nature.
Ma'am, one question.
Yeah.
Is the video? Are you recording the meeting?
Yeah, I'm recording the meeting.
Okay.
So I will share the recorded meeting through the in the Google Sheet,
Hmm.
and I shared the week 1 week 1 meeting also.
Okay, ma'am. Okay.
That is held in 30th July. So you can refer to that also. Or but I'm explaining through the lecture 1 also in this lecture.
Hmm.
Okay.
Ma'am, will you be presenting through slides as well?
Slides, no. For slides, you have to refer to the professor's lecture.
Okay.
If means I'm explaining the overview of the lectures, but you can study the professors. You can go through the lectures and can ask doubts in the discussion forum also.
Okay.
Okay.
Thank you.
Okay. So aluminium alloy has the high corrosion resistance. Means, so do you know how this high corrosion resistance aluminium get? Means it forms.
This,
Huh?
yes, ma'am. Sorry. Can I request Digambar ji to mute himself so that
Okay.
background voice is coming from his side, so I am not able to understand what you're saying,
Yeah.
ma'am.
Digambar, can you mute yourself?
Okay, ma'am. Okay.
Okay. Yeah. So.
Thank you.
Okay. So, how the aluminium has the high corrosion resistance? So, aluminium has a tendency with oxygen to form the aluminium oxide Al2O3 readily. So, when the aluminium Al2O3 layer forms on the aluminium, it is a very adherent and impervious layer of the thickness of 5 nanometer. So the adherent layer of alumina inhibit the further corrosion of the component, and thereby thereby providing the good corrosion resistance. Next is the mechanical properties. Means how mechanical properties differ according to the purity level of the aluminium alloy. So purity 0.2% proof stress or yield stress. then tensile stress, and percent elongation. So if purity is 99.6%, the proof stress is 30, tensile strength is 70, and percent elongation is 43. If the purity level increased to 99.8%, proof stress decreases to 20, UTS is 60, and the percent elongation is 45. If the purity level increases further up to 99.99, the proof stress decreases to 10, tensile stress is 45, and the percent elongation is 50. So with increase in purity level, the strength decreases and the ductility increases of the aluminium. It has the elastic modulus of 72 GPa. Shear modulus of 27, GPa, and Poisson's ratio of 0.34. So now we know that the different aluminium has different series. So our classification, aluminium classification. So first is the 1X series. 1X is the pure aluminium. So pure aluminium, if we take an example 1145. So the first two digits defines the 99%. Then after last two digits denote the impurity level in the purity level in the aluminium layer. So 99.45%. So in this way we can check the composition of the aluminium alloy. If we take the 1350 alloy, so it has the 99.5% purity. Means this means you do not means you don't have to worry about the first two digit. The first two digit defines only the 99%, and the last two digit says the points after the decimal point, digits after the decimal point. And one example is commercially pure aluminium. So as we write it like so. There are other types of aluminium like 2X series, that is of aluminium copper. So the first digit defines the primary alloying elements. So 2 represents the copper in this. In similarly for 3000 series alloy, 3 represents the aluminium manganese. Similarly for 4X, the 4 denotes the silicon as primary alloying element. For 5X series, 5 represents the magnesium as primary element. In 6X series, magnesium, silicon are the primary alloying elements. In 7x series, the primary alloying element is zinc, and in the 8x series, lithium is the alloying element. So what are the different types of impurities present in the aluminium alloys? So first we discuss about the sources of these impurities. So what can be the sources of impurities in the aluminium? So first is from the extraction process. Second is the makeup chemicals, means in extraction only we use the different makeup chemicals to get the aluminium. Third is the refractory lining. Fourth is steel tooling. So during the machining process, some impurities can also be introduced in the introduced in the aluminium. So from the extraction process, impurities are iron, silicon, nitrogen, gallium and phosphorus. In makeup chemicals, phosphorus and silicon can enter the aluminium matrix. In refractory lining, nickel nickel is not in the refractory lining, means in refractory lining oxides can enter in the aluminium metal. Fifth one is the anode carbon. Please mute the from anode carbon, impurities are nickel, manganese and iron. And in the impurities, so here with this, so the types of impurities can be elemental or inclusions, means elemental pure metals or and inclusions are compounds. So in elemental are iron, tin, zinc, copper, magnesium, manganese, titanium, chromium, vanadium, lithium, sodium, calcium, phosphorus. And in inclusions, oxides, nitrides, and carbides, etc. Different types of compounds are present in the as the inclusions. So all these types of impurities have different roles in defining the properties of aluminium. Like first, as we see the effect of impurities, so iron silicon makes the intermetallic compound as aluminium X, Fe(Y) and silicon Z. This intermetallic compound affect the tensile properties and surface finish of the aluminium. Next is the titanium, chromium, manganese and vanadium. They increase the resistivity of the aluminium alloy.
Excuse me.
Yes.
Excuse me, ma'am.
Yeah.
Ma'am, are you presenting something on the screen? Because I'm only seeing the green screen only.
Okay. Okay. Just wait. But or I will share the again. I shall share again. Are you able to see the notepad now?
Yes, ma'am, but the only green screen is appearing.
Green is green. Why?
I don't know why. I can see only the color green, nothing else.
Or you can join the meeting again. Digambar, are you able to see the screen? And this notepad screen?
Ma'am, still green screen is appearing.
Why? Digambar, are you able to see my screen?
Mr. Digambar, are you able to see the screen? I don't know why. What is happening, ma'am? Ma'am, can you reshare it?
Okay. Miss, I just reshared it. Are you able to see the screen now?
No, ma'am. I'll just share you this photo if it's possible.
Still not. Now?
No, ma'am.
What is the issue?
And
Sorry.
ma'am, you are recording, so I will rewatch it when you share the recording.
Yeah.
It's okay, ma'am.
Means I just want to confirm from Digambar if he is able to see or not. Digambar, are you there or not?
But he's not responding only.
Okay, I continue to explain, or you can see the recording.
Hmm.
Okay. Yeah. So so the iron and silicon makes the intermetallic compound, which reduces the tensile properties of aluminium, and the titanium, chromium, manganese, and vanadium increases the resistivity. And so next is the sodium. Sodium causes embrittlement in the aluminium. And the silicon cause the excessive edge cracking in the aluminium while hot rolling. So the application of aluminium alloys are first in the electrical appliances, Second is packaging industries. Third is chemical industries. Fourth one is household or architecture. So now we will discuss about the extraction process of the aluminium. So in extraction of aluminium, there are two methods. First is the electrolytic extraction, and second is the carbothermic reduction. So in the carbothermic reduction, the required temperature is around 2000 degrees Celsius to decompose the alumina, because the aluminium oxide is the very stable oxide, and it requires the very high temperature for dissociation. So that's why carbothermic reduction is not used. In electrolytic extraction method, there are two types of process: Bayer process and in Hall-Héroult process. So in Bayer process, first the aluminium ore. So what are the different types of aluminium ore? First is the bauxite. Second is gibbsite. No, bauxite. In bauxite only there are two types of. First is gibbsite, which is alumina Al2O3.3H2O. Gibbsite and diaspore. So bauxite is made of two types of minerals, gibbsite and diaspore. So diaspore has the formula of Al2O3.1H2O. Gibbsite has the alumina content of 65.4%, and diaspore has 85.4% alumina. So in the Bayer process, first the bauxite ore is crushed, grinded and classified up to -100 mesh size. Then it is leached. After leaching, it is processed through settling, then washing, filtration, heat exchange, then precipitation and thickening of alumina hydrate. So then after the alumina hydrate, in Hall-Héroult process, the extracted alumina is fed into a digester, in which anode and cathode are used to produce the electric arc. That electric arc dissociates the alumina. For dissociation, the cryolite is added. So cryolite is beneficial in dissociation of the alumina. The temperature in Hall-Héroult process is around 150 to 220 degrees Celsius. You can study the complete process in the professor's lecture, means it is properly explained. So how the alumina uh, produce alumina, alu- from the alumina in Hall-Héroult process, aluminium is extracted. The aluminium is further purified through different types of processes. First is fluxing. So fluxing is used to remove impurities in the aluminium. Second is degassing. Degassing is used to remove the hydrogen gas from the aluminium melt. So degassing can be done by mixing argon, means that inert gas purging, like argon, and the by adding degassing tablets. Degassing tablets has the composition of C2Cl6. So these tablets are used to uh, used for degassing in the aluminium. Next is filtration process. In filtration process are used to remove inclusion which as oxides, carbides and nitrides, and the solid impurities. Inclusions and impurities. So now coming to the purity level of the different types of aluminium. So first is the high purity aluminium. High purity aluminium concentration is 99.8 to 99.949. If the purity level increases further, that is called super purity aluminium. Super purity. Next is the, so if the purity level increases to 99.996 to 99.99999, so that is called extreme purity aluminium. If the purity level increases further, means greater than 99.999%, that is called ultra purity aluminium. Rohan, are you able to hear me properly?
Yes, ma'am. I'm able to hear you, but
The
sometimes I
screen,
miss things
screen
because I'm not able to see the screen and see the chemical, the chemical
like
names of the metals.
okay, you are seeing only the chemical impurities aluminium.
I'm not able to see anything. I'm just able to hear you.
Okay, okay.
And like based on that, I'm making a little bit of notes, whatever I can. And later, when you will upload the video
Yeah.
recording with the screen sharing, I will make notes then only.
Okay. Yeah, I will upload after 8 p.m. When, means after the 2 hour.
Other
Okay.
because we right now like some a lot of things are going out above my mind.
Yeah, yeah. Means there are only very few people. Two students are attending, so I'm also unable to confirm.
Hmm. And this person is not even responding as well. I don't know whether he's attending or not.
Yeah.
Because it's like right now I think that if I go through the videos on the course page, which
Yeah.
is from the week one itself,
Hmm.
I think I would be able to get grasp lot of things,
Hmm.
which is I have to complete the week one assignment as well, right?
Yes, yes.
And a lot of definition. Whatever you are saying has been mentioned in the recorded lectures on
Yeah,
the
yeah.
week one, right?
Yeah. Means whatever I'm
Okay.
explaining, that is overview of the lectures that is
Hmm.
that are studied in the week 1 and week 2. Means 10 lectures are
Hmm.
over.
Hmm.
Okay, no
What
problem.
what is happening is that whenever I switch to different tab, and
Yeah,
then once I return back to this tab of Google Meeting, it shows your screen.
yeah.
Then abruptly it goes back to green.
Don't
I don't
know.
know what is happening.
Means in my
Then
screen it is showing the complete means
yeah, yeah,
it is in
ma'am,
yeah, in my
ma'am,
screen it is
what
fine.
is what is happening when I'm going to the different tab and then
Yeah.
returning? I am able to see the screen for a few seconds,
Okay.
and then the screen goes green.
Okay.
And I
Maybe.
have reported this to the Google
Yeah.
as well. I reported this to Google report a troubleshooting problem,
Hmm.
and I don't know whether they will rectify it or not. Either it is the issue of the net or it is the issue of Google or something, because I'm not able to see the screen. It shows for a few seconds and then vanishes, and then
Yeah, maybe the
green screen appears.
call problem. It can be.
Ma'am, I want to know these online classes are what is the purpose of this online classes?
Online classes mean you can learn the course online. Means
Like it is for to clear doubts, right?
need the class you are talking about, mind class.
Yeah, yeah, yeah.
Yeah, so yeah, I'm NPTL TA. So in the whole week I get 2 hours of teaching. In that you can ask any
Hmm.
doubt, or I will explain the assignment and give the overview of the weekly run lectures. In every week I will give the 2 hour session. So you can ask any doubt,
Yeah.
or I will explain the assignment and the overview of the lectures.
Hmm.
Or if anything you want to ask about the aluminum alloys, I will explain.
Right now, ma'am, I am not done any kind of homework. Whatever you're saying
Yeah.
is I'm not able to grasp it,
Okay,
and
no
because it's my
problem.
fault, I should have attended at least. I should have seen at least 2 to 3 videos of the week
Hmm.
one before coming to the class. I did not even started my course actually. I'm also working, so I thought I will pace it according to my time schedule, so I did not see
Okay,
the
okay, no problem.
videos. And I thought this online class will be an orientation kind of thing, so I attended. I came to attend this
No.
as well. I am
Hmm. Okay, no problem. I will say, so from now you study all the lectures, you see all the lectures, and then refer to my recording.
yeah, I will refer to your recording and think meanwhile Google will able to solve this issue because
Okay.
this way you're saying you're teaching. I'm able to hear a lot of things,
Hmm.
and I've made a little bit of notes, but a lot of things have gone out of, like, I'm not able to understand.
No,
I'm
you
not
make
able to
notes
take notes
from
as
the
well.
professor's lectures. That will be good.
I take notes from the professor's lectures, and then this is it. This is the session to clear doubts,
Yeah,
right?
clear doubts and ask. Yeah, if you any doubts in the theory or any concept, you can ask, or I will explain the assignment also.
Uh, Ma'am, if you allow me to share the screen, can I share the screen? Then I go to the tab and then open the assignment page. Then you can explain it.
In the assignment page.
Yeah, if you allow me to share the screen, then I go to the assignment page, and then
No, fine.
explain
I
the
will share
assignment
the
and.
recording. Don't worry. I will share the recording. So it has.
Hmm. Hmm. You're talking about the quiz one week one assignment, right,
Yeah,
ma'am?
week one has. I thought to explain week two assignment, but no one is. Means Digambar also not studied the week two lectures, week two and week
Hmm.
one.
Ma'am, what is the
Yes, ma'am.
due date to submit the
Sorry.
assignment one?
No,
What is the due date to submit the assignment
is the
for week one?
week one.
It is on 7th, which is till tomorrow.
Yeah, 7 you can submit also now. In tomorrow.
Okay, ma'am. I will go through the videos, then I will answer the quizzes.
Yeah, means
Quiz question.
there are very short, means 30 minutes video, so you can go through them and then attend the assignment.
How to get into, ma'am, this video first week lecture?
Video, the first week lecture of the professor or mine? This record, are you talking about the recording?
Please, ma'am.
Yeah, so maybe I uploaded the lecture, so the NPTEL forum will share the recording. Recording. The I shared the link, YouTube link, so they will share the link to the to students.
So on mail ka?
Or I will share the link in the discussion forum also.
Okay, ma'am.
Uh,
Okay.
Digambarji, one question. Are you able to view the screen?
No, sir. Full screen to not be seen to be on this.
You are also not
Like
able to.
you can see the green screen.
No, sir. Green screen should not to be seen from the display. Only
Pardon?
one stand right up to black pen to be to seen on the board.
I'm not, I'm not able to understand what you're saying, sir. Is it only what screen you are able to see?
Only, sir, white screen to be displayed.
That OneNote screen.
Hello?
Uh,
Are you able to see the
Hello?
OneNote screen?
Yes, sir.
I'm not able to see at all. I'm only seeing the green screen, which is why it's very difficult for me to understand anything.
We to be sent to screen to ma'am to write up to blackboard mark to stand to the whiteboard.
Whiteboard or in the meeting only.
Yes, ma'am.
Okay, I will try. Turn on caption.
Ma'am, if you go to click the
Whiteboard. Yeah,
and
I got.
yeah,
Start a new whiteboard.
I'm just opening the whiteboard link. Mm,
Share.
You need access. Request access. I'll request it an access, ma'am. Please allow me.
Okay. In whiteboard only you sent a request.
Yes, ma'am.
Okay, let me check.
But you will get the request on your mail ID. You can approve it through your mail ID only, I guess.
Okay.
Request sent. You will get an email letting you know if
Yeah.
your request was approved.
I accepted your request.
It shows access denied.
Access
I don't
denied.
know why. I'm requesting again, ma'am.
Okay. Access updated. Are you able to see?
No, ma'am.
Means
I don't know what is happening. Something wrong with my computer today because it's like acting weird. Like now I've got the link. Okay, just I'll try to open it.
you are able to see the whiteboard.
Wait, now I can able. I'm now able to see the whiteboard, man.
Okay. And the Gambar?
Not seem to be unable to become whiteboard.
Whiteboard.
Not
Sorry.
Please check your mail, Digambarji. You might be able to. In your mail, you'll get the link to open the whiteboard. First, you have to go to the chat box, go to the link. It will open a Jamboard page. Over there, you have to request access, and then ma'am will be able to accept your request. Then you'll get a mail on your email account inbox, and where you have to check and open the link. Then you'll get the access.
no sir, not able to be to see to screen.
Or
I think he is left. Ma'am, like, would you like to what? Sorry, someone else also Monu Chandra. Sorry, it's a different. Some Monu Chandra. Hello.
yeah. Or I
Hello,
will
ma'am.
share this screen. If the Digambar is not able to join the whiteboard, I will share the screen.
Hello, ma'am.
Yeah.
Not able to see ma'am screen.
Okay, just wait. Now?
Yes, ma'am. Yes.
Okay.
Now we are able to
Please.
see.
Okay. Yeah, so I explained up to the purity level and the designation of the aluminum alloy according to the purity. So the high purity aluminum has the 99.8 to 99.949%. The next is the super purity. Is 99.95 to 99.9959%. Next is the extreme purity. That is 99.99996 to 99.999. next is the ultra purity aluminum. That has the purity of greater than 99.99. Okay. So next I will explain so in aluminum alloys also there are different types of two types of aluminum alloy. First is the wrought and cast alloys. So in wrought alloys, these series are 2x, 6x, 7 and 8x. In cast alloys, 1x series, 3x series, 4 and 5x series comes. So the wrought alloys means they can be strain harden or increase the strength by using any these are heat treated heat treatment. They are able to strengthen by heat treatment, so they are no heat treatable alloys. And these are non-heat treatable. Okay. So for the cast alloys, the designation can also be as like 1x, means the third x is gone, so means we can use the 3-digit nomination also for the cast alloys, like 1x, 2x. Means the other wrought alloys can also be cast, but the castability is less, so I will write all. For casting, this designation we use. And the other designation comes as the 1xx. So here after third digit the decimal comes, and x, we can write the x like 3 sorry 3xx point x, means the 0 after, so for example the 0 after decimal denotes the casting or near net chip casting, means those alloys can be casted to near net chip casting. Castings. And the 1 after the decimal denotes the ingot. Okay. So the In cast alloys, one series RSCD 3X, which is silicon magnesium, that forms the Mg2Si. So now we will go to the 4000 series alloy, which is aluminium silicon. So the silicon content varies from the 0%. If we make the phase diagram of the aluminium silicon, here it is 660 degrees Celsius and it is 1400. So this composition is 12.6% of silicon. The temperature of this eutectic line is 577 degrees Celsius and this is 1.65. So the microstructure consists of alpha aluminium matrix, which has the silicon content up to 1.6% plus eutectic silicon. So if we cool down, it is liquid. Here it is alpha aluminium plus liquid. It is primary silicon plus liquid, and it is alpha aluminium plus eutectic silicon. So if we cool through the eutectic point, we get the microstructure consisting of alpha aluminium and eutectic silicon. So eutectic silicon is present in the form of flake or needle type shape, so that is not required for the good tensile properties or mechanical properties, because the needle shape increases the stress concentration and decreases the ductility of the alloy. So to avoid the needle shape morphology of the eutectic silicon, modifier atoms like sodium, barium and strontium are added to modify the morphology of this eutectic silicon from needle to fine fibers. So there are two types of theory for modifying this aluminum silicon microstructure. First is the impurity induced theory, in which the modifier atoms get absorbed to the steps. Means now first, how is the growth of silicon atom occurs? So silicon forms the tetrahedron. Yes. So two tetrahedron forms the nuclei of the silicon flake. So the growth occurs as the, so this direction is 211 and they form as a king. See, so the growth happens as the twin. So this plane is called the twin plane, and the edge of this plane is called the twin plane reentrant edge. So to avoid this growth along the 211 direction, means it is only growing in the 211 direction, so it is anisotropic growth. To make the growth isotropic, the modifier atoms are absorbed to the twin plane retrient edge and the steps and kinks of the nuclei. So they uh, restrict the silicon atom attachment for the growth of silicon atoms, thereby making the needle shape sorry needle shape to fine fibrous form. So first is the impurity induced theory, second is the TPRE mechanism, TPRE restriction theory. So what is the difference between the impurity induced and TPRE restricting mechanism? In impurity induced theory, the modifier atoms attached to the edge and kinks at these nuclei, while for TPRE mechanism, the modifier atoms absorb to the retrient edge, this edge. Next is the so there are two types of alloys. First is the we see the this is eutectic point. So composition of alloy which are less than 12.6% are hypoeutectic, and composition which are greater than 12.6 are hypereutectic. So hypereutectic microstructure is alpha aluminium plus eutectic silicon, while hypereutectic alloys consist of the microstructure of alpha aluminium plus eutectic silicon and primary silicon particles. The silicon particles that are very detrimental to the mechanical properties. So that's why hypereutectic alloys are less used, and the microstructure are modified by using the alloying elements like which I discussed just now, like sodium, barium, strontium, calcium. So these are different types of elements added to modify the structure and to restrict the anisotropic growth of silicon nuclei. So now I will study that how the another method to refine the aluminum silicon microstructure is by rapid cooling. So how rapid cooling enables to refine the microstructure? As we see, the aluminum and silicon has the different thermal conductivities. If we see the thermal conductivity, aluminum is 205 and silicon has 83 watt per meter Kelvin, and the latent heat of fusion is for aluminum is 396 and for silicon is 1444. So if when the because the thermal conductivity of aluminum is higher than silicon atoms, so the cooling will be higher for aluminum, while for silicon the cooling rate is low. And the latent heat of fusion means latent heat of fusion represents the solidification temperature. So the latent heat of fusion is less for aluminum, so it will solidify early, means solidification rate is also high for aluminum. in aluminium. So what happens, like if there are two edges, first is aluminium, this is silicon, and next is the aluminium. So aluminium will grow faster, and eventually it will entrap the uh, silicon plate or silicon nuclei, and will form, and the silicon growth will stop. So by rapid cooling also we can modify the microstructure and increase the ductility of the aluminum silicon alloy. So what in the so in the wrought alloys, what are the different digits represents in the alloy? So for like 1x series, there is no specific nomenclature, means the first two digits represents the 99 and the second digits represents the purity levels, means if it is 1145, then the alloy will be 99.45. But for other series like 2000, 7000 and 3, 4, 8, and for all other series, the first digit denotes the alloying element. First digit is this. First. No, no, no. This is not. This first digit denotes the alloying elements. Primary alloying element. Means from 2 we can guess the it is aluminium copper alloy. First digit is alloying element. Second digit is represents the variation in a specific alloy. Means for example, if we see the 7075 alloy, so it is aluminium zinc alloy. So this represents if it is 7125 or 7275, then this digit represents the modification in the composition to get the desired properties or any specific property if we want. Then this second digit represents the what is the variation in the composition. Means 0 represents the impurity level of other elements, and 1 to 9 digit if 1 to 9 digit comes at the second place, it represents the it says the emphasized control of the composition. And the third and fourth digit digits are only used to identify different individual alloys. Means they are in 1x series, they have no they define only the impurity level, while for other series they used to means identify the different alloys. Means 2x, 3x, like we see there are multiple types of aluminum alloys like 4043, 4147. So this represents the just the identification of the aluminum alloy. There are very little variation in the composition, and the major alloying element is the aluminum silicon. So how these alloying elements are able to strengthen the aluminum alloy? So
Hello,
yes,
madam. Any application of the 8000 series?
8000 series alloy is the in aerospace we can see. We say that is very rarely used alloy. The it is aluminum lithium na. So the very small amount of lithium are able to strengthen the alloy up to very high level, means if we compare the like aluminum copper and aluminum zinc. So if we take the 5 or 8% of copper and zinc, then only 1 to 2% lithium will is able to strengthen the aluminum in comparison to copper and zinc in higher amount. So the lithium is a very potential alloying element for the aluminum alloy to define the microstructure and provide the strengthening mechanism. So it is it has the application in aerospace application mostly.
Okay, thank you, ma'am.
Okay. So we will now discuss about the strengthening mechanisms. So first is the solid solution strengthening. So how the solid solution is strengthening? Solid solution means the some impurity elements are present as the substitutional or interstitials. Terms and interstitial. So in substitutional they substitute the host atom. There are aluminum atoms, so this can be copper, so thereby the increase in interstitial atom can be at the interstitial site. Here like we see. So how the solid solution strengthening occurs means we know about the dislocation. So in if we see the dislocation atom like extra half plane, so this is the extra half plane. So substitutional atoms have atomic size which is equal to the solvent atoms. So they are in the dislocation. The the upper part of the dislocation are in the compression, and the lower part is in tension. To lower the stress field of the dislocation, the substitutional atom prefers to go in the tension region, or if it goes in the upper part, it imposes the elastic interaction, means there the elastic modulus will be different, means there in the so there will come different types of interaction. So first is the elastic modulus interaction. Elastic modulus interaction comes in when the atomic size difference is greater than 15%. No. First is the elastic interaction, second is the modulus interaction. So in the elastic interaction, the substitutional atoms will impose the compressive stress, and the means substitutional atom will impose compressive stress to the dislocation if and in if we see the interstitial atom, they impose compressive stress at the interstitial site, because the interstitial atom already have already are of big size as compared to interstitial. Means if interstitial site is this impurity less, so it imposes the compressive stress at the interstitial site only. So it can impose the compressive stress also, and the tensile stress also if it is very small, if it is very smaller than the solvent atom. Modulus interaction, second is the first is the elastic interaction, second is the modulus interaction, in which because of the new bonding between the alloying element and the solvent aluminum atom, the modulus will change locally around the bonding, and these are aluminum atoms. If these alloying elements come, so the bonding results in change of modulus locally. Means here locally the modulus will change, so that also results in some stress fields. So stress field due to the increase in stress field, the higher stress will require to plastically deform the aluminum alloy. And that results in increase in strength. Third is the stacking fault interaction. You know about the stacking fault how the stacking fault form? Means stacking fault form when the Berger vector of a dislocation splits into two parts. Means this, like this. If the first initial dislocation has Berger vector V1, it splits into two parts. Means these are called partial dislocations. So the Berger vector of this is B2 and B3. So if solute atoms or alloying element atoms cluster around the stacking fault, that will hinder the motion of the dislocation, and the stacking fault will never be able to annihilate further. Means it cannot change into the single dislocation. So this clustering of alloying element at the stacking fault region increases the strength of the aluminum alloy. Means higher stress will require to remove the alloying elements then to move the dislocation further. Fourth is the electrical interaction. In electrical interaction, if we know the dipole forms. So in an atom also, if due to the thermal or atomic vibration, the positive and negative charge can accumulate to a site that results in the dipole. So if this element goes into the aluminum matrix, it will impose the electrical interaction with the aluminum atoms, and that lead to the some, because of the different volumes, they lead to the strengthening of the aluminum alloy. Next is the short range order. Interaction. In short range order dislocation, if we first is the aluminum alloy atoms AA, and the alloying element has the BB bonding. So if AB bonding is favorable, then the BB bonding, that leads to the short range order. If AB bonding is less favorable than the BB, that leads to clustering of alloying element. So the short range order and clustering of the alloying element results it hampers the motion of dislocation. So motion of dislocation through this short range ordering and the clustering will require higher stresses. Next is the long range order. Order interaction. In the long range order interaction, this happens in the when the superlattice structure forms. What is superlattice structure? Is the complete substitution, means atom, there is a altering of atoms, means one is the A, second is a B, then A, B, here is B, A, B and A. So this type of bonding leads to a superlattice formation, and that is a long range order. This is called long range order. So when if shear stress is applied to this end and this location move, so atoms will shift to here, like A, B, A, B. So along this plane, the atoms will now be A, B, A. So the similar type of atoms are comes in contact as the dislocation slips on this plane, so that it results in the anti-phase boundary. Anti means this boundary is called the anti-phase boundary. So if the antiphase boundary thickness is means if the width of the antiphase boundary is high, then the energy of the this long range superlattice formation will be less. Means if we see the energy tau naught is the gamma by width of the APB. So this is the antiphase boundary energy, and this is the width. So as the width increases, the energy will decrease, and if the width is less, energy will be high of the antiphase boundary. So if energy will be high, then higher stress will require to move the dislocation further through the superlattice formed. So next is how this gamma and drag force and dislocation density. So how this motion of dislocation are able to strengthen the means can be dictated as the strengthening mechanism. Like if this is the velocity, if for higher velocities high stress will require. If we plot a graph between drag force and velocity, so that will comes as this is the width. So for a constant or defined width of the antiphase boundary, the velocity of the dislocation first increases with the drag force. So the drag force will increase with the velocity. Then after some point, when that hindrance are the hindered atoms are removed, then the velocity will increase with the decreasing in drag force. Means if we see the dislocation, so this is the if impurity atoms concentrate on the due to different elastic interaction, modulus interaction, and electrical interaction cluster around the dislocation. So when the drag force is increased, the velocity of the dislocation increases, and after some point when drag force increased to that level that these atoms are removed and dislocation is free of impurity atoms, so the velocity will increase with decrease in drag force. The another effect of increase in velocity comes with the temperature. It means if temperature is increased, like if we see the for a defined width, if we plot a drag force versus velocity, so for if this is for T1, if for higher temperature this will shift to this for higher velocity, so if so T2 is greater than T1, so for higher temperature the velocity of dislocation is high, V2 and V1. That's why we see that with increase in temperature the plastic deformation is easier, because the less drag force is required to move the dislocation through the impurity atoms. Similarly, if we see the strain rate effect is the rho VB. Rho is the dislocation density, V is the velocity, and B is the Berger vector. So strain rate is directly proportional to velocity. So if we plot the graph of drag force with strain rate, similar curve we get for distance. Means with increasing strain rate, the drag force first increases, then decreases, because the dislocation gets free after some point with increase in drag force. Okay, so next I will explain in the next. So who is the Monit? Did you attended the week 1 and week 2 lectures?
Hello, ma'am.
You did not attend any lectures?
मैडम फर्स्ट लेक्चर अटेंड किया था,
हाँ.
बाकी अटेंड नहीं किया है। आज दोनों का टेस्ट है, वो असाइनमेंट 1 और असाइनमेंट 2 दिए, मैंने आज सबमिट करवा दिए।
हाँ.
लेकिन इस लेक्चर में बहुत सारे डाउट है, वो क्लियर हो चुके मैम।
अच्छा, क्लियर। और भी कुछ डाउट हो तो वो तो यू कैन आस्क।
नो मैम, क्योंकि जो डाउट थे, जो असाइनमेंट सबमिट किए उसके रिगार्डिंग, वो सभी आपने कवर कर लिए इस लेक्चर में।
ओके, एनीवन हैज एनी डाउट? रोहन दिगंबर?
No, ma'am.
No. So can we end the lecture?
यस मैम, ओके, थैंक यू मैम।
Okay, thank you.
Hello, ma'am.
Yes.
Ma'am, I was not able to, I will attend your recording,
Yeah.
and then I will go through all the recording for first week. Then I will, if I have any doubt, then I will come back to you on the next session.
Yeah. In the
Yeah,
next
yes.
section, or meanwhile, you can ask in the discussion forum also.
Yeah, I will ask in the discussion forum as well. If you know. Yeah, thank you, ma'am. Thank you for this session.
Thanks.
Thank you.
Digambar, do you have any doubt?
हेलो मैम.
Do you have any
मैम
doubt?
यस मैम. जो फर्स्ट वीक का सेशन हुआ था उसका मैम अपना ये मिलेगा क्या मैम?
हाँ हाँ, रिकॉर्डिंग मिल जाएगा, या मैं इसकी लिंक आपको उसमें डिस्कशन फोरम में भी शेयर कर दूँगी.
ओके मैम. और असाइनमेंट का क्या है मैम? उसका असाइनमेंट का तो डिस्क्रिप्शन मिलेगा क्या मैम?
सॉरी,
असाइनमेंट क्या दिया है उसको? असाइनमेंट पर वो
असाइनमेंट
हमको मालूम
तो
होगा.
आप जो वीक 1 और वीक 2 लेक्चर्स है उनको पढ़ के ही आप असाइनमेंट दो, क्योंकि मैं अभी एक्सप्लेन कर दूँगी तो फिर आपको एफिशिएंसी रहेगी नहीं ना. पहले आप पूरे लेक्चर्स को पढ़ो, फिर उसके बाद असाइनमेंट देना. फिर उसमें कुछ डाउट हो तो वो पूछ सकते हो.
लेकिन मैम असाइनमेंट कब सबमिट करने का?
असाइनमेंट 7 अगस्त लास्ट डेट है, वीक 1 और वीक 2 दोनों का.
और असाइनमेंट का क्वेश्चन क्या है मैम? असाइनमेंट का क्वेश्चन भी हमको कौन सा
नहीं,
मेल पे
असाइनमेंट के
सेंड किया?
क्वेश्चंस व्हेन यू विल गो थ्रू द लेक्चर्स ना, ऑल 10 lectures, you will able to solve the assignment. It is not that much difficult.
ओके मैम.
Okay.
ओके, थैंक यू मैम.
Okay.